Okay, so this will be almost exactly like, well, not almost, very similar to a question that I will actually ask on the exam. For those of you who are watching via video, this is starting out with an exam review. So the first question that I ask, and I'm gonna just have to read this out for all of you guys, is going to be quite simply put on. This will be for you.
Oh, okay.
So it will say, given the component LTC2452. So this is a new component that you've never worked with, right? But it's similar to the components you've worked with in their SPY or ADC.
LTC452.
LTC2452. I will ask the question, what is the maximum number of samples per second? Note that the reported rate is rounded. What is the actual value when using typical values for the parameters? So you'll notice that you'll have like maybe temperature is in this one. It'll have minimum, typical, maximum. So use typical if you need one of those values. Show your calculations with precision to 2 decimal points. So the first thing that you're going to do is pull up the data sheet for the LTC2452. So for now, I'll turn this off and we'll come back to the overhead when I start explaining how you calculate it. So this is the kind of question that I would ask, and it took me, so I wrote the question and I went to solve it. This has, it will have 5 parts. This one will, and it will be similar when you see it. It took me about 25 minutes to do this, all 5 parts. So the first question is, why are they always terrible markers? I try and throw them away, but I feel like the bad ones just spawn. Oh my gosh, and now I can't write. For LTC, what did I say, 2452?
Yes.
What is max sample rate with precision of two decimals in samples per second? So the first thing you may notice if you go and look at that data sheet is right at the very top, it says something like the LTC2452 can sample at 60 conversions per second. So in the question, I will point out that that's rounded.
60 conversions.
Yeah, that's not the real number, right? They're throwing out a nice one. What is the actual number?
Probably more, right? When they round down rather than up.
Well, more or less. I mean, yes, but you can actually calculate this.
Well, yeah, but just like, you know, like looking at this, like if we were to look at a data sheet like this, should we assume that they're like if they're rounding it down and not up?
Generally.
Okay. Well, we need to front right.
Because if they're rounding up, a lot of times they'll say with nearly and then give a number.
Gotcha.
So, you guys want me to give you a minute to try and figure this out, or do you want me to start walking through how to do it?
What was it you said?
What is the maximum number of samples per second?
Right, what did the data sheet say?
60. So look up the data sheet. It will say that in there.
Approximately.
Yeah, so the reported rate is rounded with the actual value. So what is the actual value of maximum samples per second when using the typical values?
So you go to timing characteristics of the part, right?
That's part of it, yes.
That's what I'm looking at here.
So
is it conversion time?
that's part of it, yes.
Is that where you get the 60 from? The conversions per second?
Well, it just says, yeah, it's 60 conversions per second. So that's a sample, 60 samples per second.
Temperature 25.
Yeah. So what is the conversion time?
Min is 13 milliseconds.
Well, yes, he said you.
Typical.
16.6.
Typical.
Yeah, so I have this T conversion, which is equal to, well, I'll say about equal to 16.6 milliseconds. But then you need to look at the data sheet. So if that was correct, right, then we could say F conversion
There's one over that.
is equal to about 1 divided by 16.6, which is equal to 1 divided by 16 or 0.0166. Yeah, 62.24, isn't it?
5.
No, it's 24.
1 over 16 milliseconds?
Well,
Oh,
16.6.
yeah, you're right.
This is
Hertz.
samples
Or, yeah, samples per second.
per second.
Oh, okay.
Wait, 62 point
It's 60.
I got
Oh,
60.
60.24.
Yeah, I got 60.24.
Yeah, sorry for
Yeah.
messing you up on that.
Yeah, 60.24 samples per second. If I was only relying on the conversion time, what other time does it take?
You've got a low period and a high period.
So what is this? What is this device to do? Are we using a SPI? Or
This is a SPI ADC,
SPI?
right? So this would be one of the things that you would need to look at and
Would
figure out
you-
what it is.
Falling edge and rising edge time delay. Did you need that?
Well, you might.
Doesn't really give anything.
Isn't that very slow?
This is a very slow,
There you go. There's a
very
timer.
slow but very precise ADC.
Okay, gotcha.
Would we need the, like, well, I guess it doesn't really have any, like, does it have any overhead?
Doesn't.
Right.
So that's actually one of the later questions, right? So if it kind of helps, I'll write up some of the other questions that we can come back
Go
to.
to page 9.
Oh, we would need the rising edge and the falling, we would need to add one rising edge and one falling edge, in there, right? To get the beginning of the end.
So not quite.
27 full time.
Not quite. So if you go look at page,
Page 9.
nope, we're gonna go further than that.
I don't want further than that.
Let's look at page 10.
Application information.
Yeah. So on page 10, it shows that there are three different time periods. There's the convert time, there's a sleep time, and then there's a data output time. Now, reading through that data sheet, it turns out the sleep time is optional, right? The sleep time can be virtually nothing. What I do have, though, is the time to send the data.
Oh, we got it.
This is page 10.
After the 16th bit is read, we get to
Well, you just look at the plot, right? Convert, sleep, data output, then go back to convert. So if I take 16.6 milliseconds to convert, I then need to take some amount of time to send that data out. So I convert, I get it, now let's transmit.
Oh, so that's not actually, oh, okay, I
Yep.
understand.
So do we need to add one falling then?
Not quite. We need to add, well, how many bits is it? It's 16. I need to take however long it takes to send out 16 bits.
Times however long each bit is.
Yes, exactly.
Oh, so that T conversion is not this right here. The conversion happens before that.
Yeah, so there's conversion, which it takes an analog and converts it into a digital number, and then we need to send that number.
Okay.
So how long does it take me to send that number?
So 1, 2, 3, oh, okay, so 16 times e to that. What's that?
How long is the bit? It's a real question. Ships like falling.
Yes, we got to go back up to the timing characteristics.
Yep. Yeah. So we'll look at the timing characteristics.
So the low period, the minimum is 250 nanoseconds, the high period is 250 nanoseconds.
Yep.
And then the falling edge to low Z, well, we don't need to worry about low Z, right?
Correct.
And nor high Z.
Correct.
CS falling edge to SCK falling edge, we need to say about that?
We could add that in or not, right? Because I'm only asking two-digit precision.
Let's just show it to us, like how we would do it.
Yeah. So this is how long it takes to convert. Now I have, you read it. So there's two different ways I can get this number.
Yeah.
One of them is that the clock speed max is equal to 2 megahertz.
What does it say that?
I think it says at the top, doesn't it?
It's on page 4 in a table. It also says
Clock frequency range.
Oh, okay.
Max is 2. Okay, I got you.
that clock high and clock low times are both equal to 250 nanoseconds. But those are tightly linked, right?
Yeah. Do we really need the clock now?
Well, you need either one of these two,
Okay,
right? Because a maximum clock frequency of 2 megahertz says this is true.
okay.
Yeah.
Yeah, because 1 divided by 500 nanoseconds is 2 megahertz. So with that, the real one then is I have 1 divide. So this is F sample max is equal to 1 divided by that 16.6 milliseconds plus 16, because there's 16 bits, times the period, which is 250 for high plus 250 for low nanoseconds, which is equal to 1 divided by 16.6 milliseconds plus 16 times 500 nanoseconds, which is 8 microseconds, which is equal to 1 divided by 16.608
Does that change the,
milliseconds.
does that change it out?
Maybe, maybe not, but my number ends up with that should be equal to 60.21 is my maximum. So it does.
Where does the 8 microseconds come from?
That's the 16 times this.
Oh, 8 microseconds. Okay, here's the top. Okay.
So it takes me 8 microseconds to transmit out the 16 bits. It technically takes me 8 microseconds plus 200 nanoseconds because of the setup, the
Yeah.
CS rise and low.
So man, it's just shooting those numbers out, isn't it? It's just shooting those numbers out. Like it takes like 0.03. The difference in the hertz or the frequency is only 0.03 hertz.
Yeah. So it's really small, small amount of time to send that data.
Mhm.
Takes a long time to convert the signal.
Gotcha.
Okay. I see people are still writing, so I'm going to give them a second.
So if you were to like throw this into like dead heat night class physics 2 formula, it would be F max is equal to 1 over F conversion plus N, or like the number of bits times low.
Okay.
So it's unfortunately not that simple
Mhm.
because certain ADCs, depending on the way they work, they will take the first bit and they will, all they'll do is they'll use circuit reuse where they'll go, is this bit higher or lower than the midpoint? And if it's higher, it produces a 1. If it's lower, it produces a 0, right?
Yeah.
And then it subtracts out that reference and ask that same question again to generate the next bit. So it only has one converter that it keeps feeding that back into and asking the question, is it higher or lower, and generates the bit stream. In that architecture, every time you make that decision, you can send that bit out. So you can actually start generating the data before you finish the conversion in some of these. So I will provide this sheet that I'm going off of. I'll post it as kind of the review. And another question gives you another component and asks you to do all of these same things for. So this is just one component, because I will give a question like this that I want you to be able to show that you can dig through a data sheet to create clocks and SPI and that kind of thing, right? So the next thing is, if my application requires that I use 5 of these ADCs, how many pins, inputs, outputs, or in-outs, or each of those, and in-out, do I need for my FPGA to interface to these 5 ADCs?
How many pins is the 5
It's fine.
So if I'm saying if I'm designing for an application with 5 ADCs, how many input, output, or input, output pins do I need? So I would expect an answer that would say I have some number of ins, some number of outs, and some number of in-outs.
So
What are those numbers?
you got one output for the clock regardless of how many chips you have, right?
Yeah.
Then you have one for the data. And then you have one.
Well, those are outputs, sorry.
What is the clock? Yeah.
Because you're sending this data to every single one, correct?
Yeah.
And then you've got,
Wait, so
and
this
like
is
the number of chips.
A?
This is for the FPGA. What are my pin allocations?
Yeah, but this device, I guess.
That's an AD, yeah, this is an ADC device.
Okay, ADC, okay.
You need 5 chips alive?
Yes, I need 5 chip selects.
And then you don't need any in and out for this.
Tell me I started recording, because sometimes I forget to do that. I did. Okay, cool.
0 in and out for an ADC.
Yes, 0. For this ADC,
Yeah.
0.
And then you need a V reference VCC, which I mean, I guess if you're asking for that.
Well, it actually, in this one, I also need 0 inputs.
Okay.
Because oh wait, no, sorry, I need 1, shoot, no, not 0 inputs, what was I thinking? Clock data, this is where I got led astray. Data is not an output. We're not sending
Yeah,
anything to the
yeah,
AC.
Okay, because I was gonna say, I was like, hold on.
Yeah, sorry, I get caught up in what you guys say and I'm like, haha, you guys, no. Yeah, so I have 1 input data line, because they can all share a data line.
Oh,
So-
but it's, okay, that's right, because there's a Mimo and Mosi.
Yeah.
That's right.
But this one actually doesn't have a MOSI. There's no master out slave in. This is what we would call strictly a 3-wire SPI. Because the only data transmitted is from the ADC back to the FPGA. There's no configuration registered for me to
Okay,
write
so
to.
we can't send any data to the
No.
ADC, okay.
Yeah.
all right.
So how it's working is, the FPGA is controlling specifically which ADC it's listening to at one time.
Yeah, via these 5 chip selects.
Yeah.
So
Right.
it's got one in that they're all tied together, right?
Yeah,
But it's only. Oh, but that chip select.
I will draw this.
One output, I got it. now.
Yeah.
Okay, that's what it said.
Do you need ground and power on that?
no, I would not count. If you put ground and power, I would probably get confused and mark it wrong, and then you could be like, oh, but I was counting ground and power and give you points back.
Yeah,
Because it's not wrong, but we don't, remember, anytime we write
Ground
our
and power is
constraints
different.
file, we never put ground or power, because those are kind of like dedicated pins. So, and ground and power is not really an in or an out, it's a supply, which is a kind of different.
Because you could run it totally not supplying it from the FPGA, as long as they have it from the.
Okay, so the types of chips we work with are 82. DA2s, ADCs, or is that just an ADC?
Sorry, one second.
Okay.
So I have a data line that can be shared to all of them. I have a clock line that is shared to all of them. And then I need CS0, CS1, CS, and in this case, I'm only doing 3. Right?
For a total of 7.
Yeah, so 1, 2, plus 5. This number changes if I'm using like an I2C, right? Which I might likely ask some question like this. Like here I could further the question like, if I were, how many wires could I save by changing this device to an I2C?
4.
Well, we have to think about that, right? So it is no longer using any of the CSs. So we get rid of all of those. But now I have to write data. So depending on how it goes, we could have a single data line that is an IO. So now I would have one IO.
Or data in, data out.
Yeah, for D in, D out, and a clock.
Okay.
So I'd have one IO and one out. Yes.
Okay.
And then I could go on and further ask, okay, so now I have an I2C. I've saved ourselves 5 lines, but I have a 4-bit address to address these devices. Now, what is my maximum sample rate?
Oh, no.
Right? It doesn't actually really change very much because I'm just adding 4
You
bits.
have 4 bits, yeah. So
Add
it's
4
just
bits to
gonna
the
be-
16, and it may not even change that number. But I would ask you to show me that math. And I would have to say something like, assuming that the conversion time doesn't change, right? Which is, it probably doesn't because it's still 16 bits. We're just sending out 4 more bits in the register.
Can you do a quick find out if I kind of tips these down? Because I have not clue on any of them, to be honest.
Okay, so it all comes down to, we've designed a Uart.
So UART is the one that sends data to a computer.
The Uart is our asynchronous,
No clock.
no clock. Well, we have to know what the clock speed is beforehand.
The baud rate has to be
Yes,
defined.
yeah, so a defined baud rate, asynchronous communication, it can start at any time, stop at any time, and the send and receive are dislocated. There is no master, there is or slave, right? Then we have the SPI D to A, digital to analog converter. Then we have an I2C analog to digital converter. That's all we've really dealt with. Now, when I ask you questions, I can mix it up just like I did here, right? So here I had a SPI ADC. What you're used to working with is I2C A to C. So I might mix those around. So the question might have an I2C D to A.
Okay, wait, the SPI is the one that we like.
Yes, yes. So we have ADC, DAC, SPI, I2C, and I may mix and match those any way I want.
Okay, so
And then the next one.
ADC is analog to digital, DAC is digital to analog, SPI is good, I2C is bad.
Yes, well, depending what you need.
No,
Low wire
SPI is
count,
bad.
or sorry, low wire count, high wire count, low overhead, high overhead.
How does that make sense?
What?
No, sorry.
Okay.
I think I did my math wrong.
Yeah, so you're just, the only thing you're changing is it's 16.6 milliseconds plus 16 or 20 times 500 nanoseconds. So it's changing it by 4 times 500 nanoseconds. So 1, 2 microseconds.
Okay, so my number's right. You go from 60.2119 to 60.2047.
Yeah, it doesn't change very much.
So
You're
yeah,
only
not
having 4
really
bits at 2
anything.
megahertz.
Yeah.
Okay, next question. Using the data sheet, is the SPI data collected on the rising or falling edge? Yeah.
How did the 2 megahertz factor in?
This and this are linked. You can get this plus, oh, I erased it. The
I just want to make sure because I wasn't seeing where the 2 megahertz.
yeah, so the equation ended up being
Looks like
plus
250 plus 250.
So I could either take the clock high, clock low and add them both together, or I could put 1 divided by 2 megahertz.
Okay, so 500 nanoseconds is the same.
it looks like it's on the rising edge of this.
Where'd you find that?
The page 12 or 11 or 12. It's just that's where.
Yeah, so a reminder for the next question is the data collected on the rising or falling edge of the clock? We'll give them a second to work through it. So the way that generally I would address this is I would go and look at the timing diagrams, and that gives you a hint. But here we have to be careful, because you'll notice that each one of these actually defines in the figure underneath, it says CPOL equals something. So if you actually scroll to page 13 and look at those timing diagrams, what you'll notice is that you can have CPOL as 1 or CPOL as 0. Now you might ask yourself, what does that mean?
That's the state of the clock when idle.
Yes, the resting clock. So it actually turns out this one, you get to choose whether you want to read the data in on highs or lows based on where you rest the clock while CS is high.
So if it's high, then it's on the falling edge, and if it's low, it's on the rising.
Yes, if you're resting high, it clocks in on the rising edge.
Okay, so when you engage or disengage CS, where your clock is.
When CS drops, where is the clock?
Okay, so, all right, so if it drops and you're low, then it's gonna be the rising edge that triggers it?
Yeah.
Or if you drop.
Yeah, if you drop while it's high, rising edge. If you drop while it's low, falling edge.
Okay, so that way it gives it one full clock cycle.
Yeah.
before it-
Yep. Yeah, so it can be either edge triggered, which is actually really interesting. State machine. And a fun question, if I was being really hard, would be to design a state machine that can be either rising or falling edge based on this criteria. Right? That would be a fun design. But
You can look at it.
That would be terrible.
it would be, but it would be really
No, it
interesting.
wouldn't be terrible.
You run into some interesting challenges, but
Wouldn't it just like pretty much revolve around like essentially hooking up to an AND gate, and then like setting a B flip flop for once you engage it to go into that AND gate.
maybe, not
And then
really.
set that equal as your like.
But you have to be able to, this can literally change on the fly with no configuration changes, really.
Yeah.
So that one can be interesting. Okay, so that one was a bit of a trick question on this one. So these kind of get interesting because I wrote these questions and then I went and found a device to try and answer them just to see how long it would take me. So some of these questions are potentially weird because of the particular device I chose. When I write the exam, I'll be sure to make sure that they're clear for the device.
Of course, I guess I'm just still semi-confused on the whole, how we figured out from this diagram right here.
So that diagram right there, that's the 13.
Yeah,
So what you can see there, so the main hint is that it has different CPOLs,
I understand
which
that.
you can jump to the conclusion that obviously it can change.
Okay.
The other thing is that you can see that the rising edge on the top figure is in the middle of the data, and the falling edge on the bottom of that is in the middle of the data.
Okay, so it's collect. Oh, okay. So just go off based on, we want to sample the data in the middle, so just go off
Yes.
what happens in the middle. Okay.
Yeah.
So CPOL is equal to 1 is rising edge.
Yeah.
Okay, thank you.
Okay, then the next question is, so this one has either 2-wire or 3-wire configurations. You can actually just tie the CS to ground and just ignore chip select. So I would have to specify. So in this next question, in 3-wire mode, what signals the ADC to start a new conversion? So we're going to look through this. This is where we start kind of looking at the applications specifications or timing diagrams. You can often get this from multiple places.
Wait, so are you saying we are, that we can control chip select, or is it grounded?
So I say you do control chip select.
Oh,
So 2 wires you don't. 3 wires you do have a chip select. So in the case where you are using chip select, according to the data sheet, what signals the ADC to start a conversion?
The clock signal goes up. And then data and the data out and clock. But then you say the high order. That's data high needs to be high and clock or subtract needs to be low.
Careful with the timing diagram because that one can get confusing.
If I'm in applications.
So I would go to, in this case, so this is why it took me so long, is because in an exam, I'm going to give you time to read through the data sheet. So I don't expect you to just jump to right where it is, because it changes based on data sheet. But I do expect you to be able to just comb through this and kind of find that information. And I will give you more time in my estimates than I took me. So I measured me at 25 for all 5 of these parts that I'll go through. I would give you at least 50% more than that.
So it's just triggered using the chip select signal
Yes.
according to page 11.
Yes. So, and you can start reading this on page 9 is actually the most clear one. And it kind of sucks, but it can be valuable to actually spend the time just to read the whole data sheet, like just the whole thing when you're addressing a question like this, when you start doing it. And I like that, and I will give you time to do that, because realistically, anytime you're working with a new device, the first thing that I recommend doing is reading the whole data sheet cover to cover. You don't retain it all, but sometimes you're like, oh, I read something about that. And if you're on your computer, you can do Control F and search for one of those terms, you know? So like, oh, the CPOL thing popping up. What is CPOL? Oh, there's the data app note on it, right? So here you can search for convert. So I when I was doing this, I searched for CONVER, and I left off the T for convert, because I might have convert or conversion, right? And then I just did a search through this until I found a spot that I liked that was talking about it. In this case, starting at the very bottom, page 9, and jumping onto the next one, so it's really at the top of page 10, it says, after the 16-bit is read, the user can choose one of 2 ways to begin a new conversion. First, you may pull CS high, or you can just give it another clock.
Wait, what? So you can just pull it high and then just keep reading?
No, if you pull it high, it will do another conversion. And then to read that conversion, you drop chip select back low again. Or you can go into continuous read mode and just keep providing it with the clock while holding chip select low. So there's two ways in this one in order to tell it to give me more data, to do another conversion.
So the way that, so are we asking like to send data or are we asking to like convert? Like,
Convert. The question is to convert.
which in this case, you just pull CS5.
Or give it a 17th clock. Yeah. Okay, so this one ended up being a really bad question for this device because of how long the conversion takes. But if I define overhead as any time spent that is not spent sending the 16 data bits to me, what percentage of my time is overhead? So this one is a little bit tricky because, okay, if I define overhead as any time that is not spent transmitting the 16 data bits, what percentage of my time is overhead? So this is not necessarily great because conversion time is not really overhead, but it's still a fine question.
So are we including the conversion time as overhead for
Yes.
now?
Yes.
So you take the time, you'd add both those times up, like the total time, and then you take the time that it's actually sending data and put it over that.
Yep. Yeah, so what he just said is, what you do is you take this 16.6 plus this, add it together, that's your total, and then you just do the percentage that is not this, so 16.6 divided by the sum. And you end up with like 99.95% of it is overhead.
Nice.
Slap a government sticker on that, call it, give it a contract.
So
Why do you always have to say actually?
probably because you have lots of terrible
I
jokes.
know.
Okay,
I was saying that more in the sense that.
so those are like the 5-part question that I like for SPY. If you would like more practice on that, I recommend doing the same part or the same process. This part is very similar but different enough that you would have to look at it because this one actually does have an address in it. So this one is the other part, ADC 124S051.
So conversion time, max frequency, in out.
Yeah, I'll post the questions.
Oh, you are?
I will. But this is another good part to practice the SPY type on of those types of questions. Pretty sure it's SPY.
9.9995.
Actually, this one, I don't know if this is, I don't remember. I just looked at it and go, this is a good part that I might ask that question on. So that's the one, this ADC 124S051 is a good practice question. And we may, depending on the time and what everybody wants, we may come back to this one and do those same questions here. I could do the same kind of process for like a D to A or an ADCE with I2C questions, right? So let's think about the D to A section if it was a D to A I2C, right? So we've used I2C for ADC. So we did this, right? Now let's imagine what would happen if I gave you that, an I2C D to A. And I asked you questions like, what percentage of your time is overhead? Well, now you have, the D to A doesn't have that ridiculously long conversion time.
Yeah.
But what does count as overhead is all of those acknowledge bits and the address bits right? And in that case, you might even have to factor in, depending how long the packet is, the start and stop conditions. Because those are not transmitting data either.
Yeah.
You get most of the points if you ignore those, but that is something to consider, is that that is part of the overhead.
So you're stating more in general ADCs.
It really depends. There are many different ADC architectures. The ADC that I gave you guys for this first practice one, its whole thing is that it literally continuously checks the offset to make sure that there's virtually no offset, which is really accurate. So it's very precise, but the trade-off is it takes a long time. There are other ones that are very fast, which generally means that they're bigger ADCs. They take up more surface area because they do multiple checks at the same time. So I described one of them, which that just for each step of the way, it checks and sees is the signal bigger or lower than this reference, and then it cuts the reference in half and says, is that next section bigger or lower than that? That's it, right? And so that goes step, 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 step. But you could imagine
Do all those steps at once.
do all of those steps at once and just say, what is it? And then it's much faster. It's a way more expensive ADC to do it that way. And it turned out they're actually less precise, but yeah. Okay, we may come back and do another example, but that's the general idea of the I2C, is that if I'm doing I2C D to A, you're gonna have a different way to calculate overhead. And you may not, I mean, depending on your chip, you may or may not get that kind of hint at what the maximum sample rate is, right? Okay. Next question. I don't necessarily think I need to walk through this like too pointedly because it's fairly, hopefully trivial if you have the book. The question just ends up being, so it says, find the encoding for the Mips instructions below. And all that's asking is, it's going to give you a table. And it's going to say, if I want to subtract, shoot, I might have to take more than that. 7, 5, 8, blah, blah, blah. Right, so given this command, write out the hexadecimal code for that. And that's literally just go look it up in the book. Yeah. It could also, I could give you commands like this and ask you a two-parter of write the hex and ask you what does it do, right? Or like, what's the difference between add and add I, right? Add is I take it from 2 different registers. Add I is I have 1 register and an immediate value. Okay, so this next one.
So there's Mips, and is there another one?
There's tons of other ones, but Mips is the only one you have to concern yourself with. Okay. So. Next question. Consider a 5-stage pipeline Mips processor. This wording may sound a little bit confusing, but I'll come back and cover the wording just so you're clear, and I will not be this unclear in a question. But so it says, assume a write-through register file, but no other forwarding paths. We haven't talked about forwarding paths, so that's why I would say don't worry about forwarding paths, just in case someone knows what they are from other contexts. Complete the pipeline diagram for the fragment below. So, I'm going to skip the $signs. Wait, no, that's not fair because it can get confused. So I want to execute these commands. And I want you to fill in the pipeline diagram, what it should look like for these three commands. Now, the main thing to look out on this question is that, right, so remember what these instructions are doing. And if not remember, then go look them up, right? What it's doing, the add immediate is adding whatever is in register 0 plus 24, because that's an immediate value, and storing it in 6. And then down here, I want to use the contents in register 6 and then put it in 7. So 8 will assume, well, we don't do anything with it, so it's already available, right? But we need to make sure that 6 is ready by the time that I want to use 6, it needs to be updated. That's our big kind of gotcha, kind of, right? Because otherwise we would just write fetch, fetch, and push them all, right? But we can't do that. So what I would do is identify the problem location, which is 6, and then identify at what point will this be ready. Well, we know at here is where we're storing it back in the register. So at this point, 6 is not ready. It will be ready the next clock cycle. Yeah.
So the step that we need it to be ready.
I can't read and write from that register on the same clock
I
cycle.
understand that, but couldn't you, my question is, which of those 5 steps is the one that register 6 needs to be ready for?
Absolutely.
Because we can fetch the instruction, decode the instruction,
Yes.
and I don't remember off the top of my head what EM and
Execute.
Execute. Okay, so execute's the one.
Yes. So execute has to come in the cycle
Yes.
after
Okay.
this one. Now, there are no other what we call dependencies for this command.
Yeah.
So we can fill back in this one and just fill in from there. There's my pipeline diagram. Right, so what we're looking for is dependencies. Yeah,
So that second one, could you also have it shifted over one and no?
sure, why not?
Okay, all right.
Could you have it starting at the same time? No.
You cannot start at the same time. Because if I did that, I don't have multiple fetch circuits.
Gotcha.
So how did you know this number's like 6 and 7?
Because here I'm saving to 6 and here I'm reading from 6.
Oh, so it's when it's supposed to be.
Yeah, if I'm trying to write something in there and then use it later. And so I stole this from Dr. Brown, and I immediately had that same kind of thought of what's the issue. And so I should, if I'm responsible and careful, I will go make sure that question says something like, assume that all registers start at these values, and assume that my final value in register 7 should be 42. Right? Because there's not actually necessarily something wrong with this unless I specify that I need this value to be what's added. Right? So this is missing a little bit of information from what I should ask correctly. But it was still written this way from an experienced professor. Dr. Brown knows what he's doing, and he still kind of left that ambiguity there. I will try to avoid that ambiguity. So I could say that N8 has the number 24. All of the registers start at 0. and I want 7 at the end of this, 7 should equal to 48. So at the beginning of this, every other register is 0. So if I don't wait for that, 6 is at 0. And then I would have 0 plus 24 is 24, and that would be wrong. This diagram would make sure that actually added up to 48.
So this seems like almost like too straightforward.
Nope, it's really that easy.
Like, because when you're doing those, if that was the case, can you just do like the F through W, shift it over, move it down, shift it over, move it down? Like regardless of the question of that?
No, because of what we just talked about, where you need register 6 ready before you can read from it again.
Okay.
Yeah, so I need to make sure that we get the result we expect.
So then,
And I should also say something like in the minimum number of cycles, because otherwise you can just offset these by a huge amount and then you know you're going to work.
so which one, I must have blanked over this. Which one of those, like the fetch, decode, and code, which one of those makes it ready? Right?
Right,
Yes.
right back. So
And it's that,
memory access, right back to the register.
okay, and so why is that after fetch? Is it encode?
So fetch gets the command from the process controller,
So
says,
fetch
what am I
command.
doing?
Okay,
Essentially, or get the command. Decode is, what does that mean? And it
Okay.
gives commands to send out all the control signals. Execute is do an arithmetic, which if I'm accessing memory, do arithmetic is don't really do anything or provide an address more likely,
okay,
right? So E is provide an address to memory, and then write back is take that whatever is in that memory location and store it in a register to be ready to be
Okay.
used.
so that, the E just needs to be after that W.
Yes.
Okay,
E, no, the E, well,
not that E, the E below it.
yes, the E, this E needs to be after that W because they have what we call a dependency.
Got it. This may be another off-topic question, but do you have to have them in order? Like, can you have like an F, D, and then like a couple spaces, E, M, W?
You would always write them going this direction,
Yeah,
like this. And you need the operations all in the correct order.
okay, but could you do like 0, like F at 0, D at 1, E at 3, and 6?
Oh, so you're saying F, D, E, M, no, you cannot skip.
Okay,
That would just
Well-
waste a clock cycle.
Yeah, well, so this is where that kind of terminology that I mentioned at the beginning that we haven't covered is forwarding paths. So you can develop what they call forwarding paths, where you would take, say, E, and so we don't need to save E in memory, and we're gonna use it really soon in the write back, and I know I'm gonna need it. So let's say that we could add some logic that says, okay, I've got something coming where I'm gonna need it. Let's immediately feed E into W and skip ahead on that one if it's available.
yeah,
Right, and you can start speeding up clock cycles on these dependencies when you know you don't need memory.
gotcha.
So, and the book will talk about that if you're really curious. You can go in and read it, and it talks about a little bit about forwarding paths, and it talks about how you don't always need the memory stage, which is a big deal because memory is the slowest one. Okay. All right, I like this one. So I'm going to provide some timing requirement or timing specifications for a microprocessor, and then ask, based on those timing specifications, what is the maximum clock speed that it can handle? So the memory has a setup and hold time of 200 and 100 nanoseconds respectively. So setup is 200, hold is 100. The ALU delay is equal to 50 nanoseconds. Both fetch and decode have delay 30 nanoseconds. Registers set up hold of, what did I say? 50 nanoseconds, and a clock to Q of 80 nanoseconds. And all other components can be considered ideal. So this is really just a timing question in disguise, essentially. And I haven't answered this one yet, so there's a chance I screwed this one up, and we're going to run around in circles for a second before I realize I'm kind of dumb.
So start with the fetch.
Yeah, well, let's start by identifying where our likely problem is.
Shouldn't we identify what's the instruction that takes the longest first? Because that limits us.
Yes, but we can kind of skip ahead of that because what instruction does take the longest is essentially the memory, right? And to use the memory, I have to access the memory through the ALU.
Oh, that's right, because every single instruction has those 5 regardless.
Exactly.
If we need them.
Yes.
Okay, so every instruction takes the same amount of time.
Yeah.
Okay.
Yes, and so this is not quite wholly correct because what I've done is I've said the ALU always takes 50 nanoseconds, but it will take different amounts of time depending on the operation. And it actually happens that the memory action, which takes the longest to actually execute, takes the shortest amount of time in the ALU because there's no actual math going on in there, right? It's literally just passing an address directly from a register. So it's literally one clock to Q of a D flip-flop. But we'll just say that ALU has 50 nanoseconds.
So yeah, just like Jason was saying, we'll have fetch, decode, and then we're gonna get to execute.
What's the question again?
What is the fastest that I can run this clock? So I'm gonna have one clock per step in that pipeline. How fast can I run that clock?
One clock per step.
So I have to figure out what my longest delay takes. Well, my longest delay is
Memory.
300.
I'm gonna have an issue at the memory.
Yeah.
So I need to make sure that I meet setup time for the memory, which is coming out of the ALU.
Yeah.
Fetch and decode, they're gonna go by really quick, we don't care. We can look at that number and just throw that away at this point.
So
Because fetch takes one clock cycle, that'd be 30 nanoseconds. That's decode is one clock cycle, that's 30 nanoseconds. So the clock cycle that the ALU has to resolve in is 50 nanoseconds. So if I have essentially this, if you go back and look at the book, right? And this registers also has other inputs. So this is the basic structure of what we're looking for. This guy, we can just more or less consider it to be a DQ flip-flop, right? Because that's what registers are. It's just a bunch of DQ flip-flops. And so we know that when a clock happens, it takes, or I say 80 nanoseconds to update from whatever's here to put it on the queues.
we have to wait at least 80 nanoseconds so far.
And then we have a delay here of, what did I say? 80 nanoseconds. So it takes 80 nanoseconds from when it gets the data
Oh, okay, gotcha.
to when it's ready for the memory.
So is that the fetch and the fetch and decode plus the ALU?
No, isn't the ALU, I said it. Oh, ALU is 50, sorry.
Oh, so that is the ALU.
Yeah, that's the ALU. ALU. That's the generic symbol for an ALU.
Okay. We'll pick them up and find them out.
Yeah, with a little divot. So we know that there's essentially, just visualizing this, there's a clock that happens here, there's a clock that happens here, and there's a clock that happens here in order to execute each one of those. So we need to find somewhere where we need to make sure that the operation finishes in time for the next component to be ready.
So I feel like with the 200, 100 nanoseconds, isn't that pretty much the answer right there? Like, isn't that the only thing that is the same?
Well, that's the big numbers is a good thing to start looking at. So what that means is the ALU has to be ready 200 nanoseconds before this rising edge of the clock.
So the clock period like would be 400 nanoseconds. That's the fastest you can have it done.
Well, let's check, actually. Because what could happen, depending on what these numbers are, right? This clock happens, it takes a while to update this queue.
Yeah.
And then the ALU has to execute whatever it's doing and then provide the number for that setup time. So I suspect the setup time is actually going to be a little, it's going to be, it might be 200 plus something.
Okay, so you give the command to the register and you don't wait for that. I'm having trouble with time.
Well,
Or do we work backwards from the memory?
I think either way will work. Do you want to try and work backwards?
Sure. So we know that the memory has to be, setup time gives us 200 nanoseconds to do whatever we want in the ALU in the register, right?
Or doesn't the ALU have to finish before the 200 nanoseconds starts?
Well, if the ALU is done, and then from the time that the ALU is ready,
Yeah.
I need 200 nanoseconds.
Oh, okay.
okay,
So you'll
so-
be taking 200 nanoseconds and adding 50 no.
Well, let's work through it, right? Because this isn't obvious,
Yeah.
and I haven't done the answer. So it's worth considering the timing. Because
Okay.
timing, I know, struggles with you guys. And I'm not always perfect with it either. So let's do it. So I need the ALU. So let's say that this is the clock cycle upon which I execute my memory operation.
Good.
I have a setup time before this happens of 200 nanoseconds,
Yeah.
wherever that falls. In this, oh, not a capital N, that's newtons. Okay. So that means that this clock here has passed something to our ALU.
Right.
So our ALU gets it, this plus,
Hold on, how did we determine that is the clock?
I'm defining this as clock.
Well, I know, but how did we determine that that was the clock that the ALU gets the thing?
Because the ALU gets it. Oh, you're right. I see what you're saying.
But we're assuming everything else is ideal, so.
Yeah, no, you're right. So this is the clock that gets the
Yeah.
updates the.
That's what I was.
The ALU,
thinking.
yeah.
That makes way
Sorry.
more sense.
So this clock happens, and this clock plus
50 nanoseconds.
50 nanoseconds is how much time it takes for here. So I need essentially the space between this clock and this clock
To be 250.
to be 250 nanoseconds.
So, okay, so you could really do it in less than, so you would do 250 nanoseconds is the theory then?
Yes, my maximum clock speed is 250 nanoseconds.
Well, yeah.
So 1 over that is 4 megahertz.
Oh, 2 megahertz.
4 megahertz.
4 megahertz. Probably like 2 times that. So when you say delay, is that just like a hold time pretty much? I think that's what just kind of.
Oh, it's because the ALU specifically has no sequential logic in it. ALUs are combinational. So it has a delay, not a setup, hold time, and clock to queue.
Okay.
The fetch and decode might be sequential or combinational, and really they're usually a mix of them from what I've seen. So you'd set those up and like with combinational logic, but it's too fast essentially. So you need to separate them by a sequential logic in order to deal with the clock.
Okay.
That makes sense to everyone?
Yeah.
250. Yeah. And it really just starts from drawing a clock and trying to figure out, I mean, I actually like the approach we ended up doing and start from the end and then kind of push it towards each other to see what you need, right? I did like starting from the end. I thought that was helpful. Okay. I feel like this lecture is like, even though it's a review, it's just crammed with information.
Yeah, well, I'll be honest, a lot of this stuff I've been meaning to go back and study, but I just haven't had the time.
It's fine. You know, we're reviewing it in preparation for a week, and I haven't been assigning a lot of homework.
No?
To be merciful, but it also has the penalty of you may be less prepared for this. So there are trade-offs to what I've done for you guys. So I'm trying to make sure that the review is clear and educational.
Thanks, Steve. I feel like I understand the stuff, but I just don't know how to answer questions about the stuff. Does that make sense?
Yes, yeah, no, I get how that can happen. Okay, in the similar realm, I have a note. Let me make sure that the note makes sense. Sometimes I'm a little scatterbrained. Yes, the book on page 466, problem 9.19, parts B and C. Don't worry about part A, really.
9.19?
9.19, parts B and C. And I'll post this sheet that it mentions this. Parts B and C, it has a question, how many cycles does it take to execute n instruction Cs with no dependencies in a Mips? And then C is how many cycles does it take to execute the following instruction sequence? Right, that's the same kind of question that you can go through. Good practice problem in addition to what we've walked through on the board. Oh, I like this question. This is more conceptual. If I were to combine the fetch and decode stage, which happens a lot, we can fetch and decode at the same time. And I just drop the memory access. Let's say I have a microprocessor that never remembers anything. It just executes strictly off registers. First question is, how many stages would my pipeline be if I did those two actions? I combine the fetch and decode, I drop memory.
That'd be 3.
3 stages. So then, ensuingly, how many commands can I execute simultaneously without repeated circuits? 3. Because I would have I could have fetch and decode going on for one instruction, execute for one instruction,
Right.
and write back for one instruction.
And
So
then that
my
would be
pipeline is full after 3 instructions.
Gotcha. So this is just a more of a request. Can you give us almost like a graph sheet if you do a question like this?
Yeah, I will, it'll look exactly like, it'll have stuff like this.
Okay, sweet.
Yeah.
Golden.
Okay, here's another good one. A system acquires new data from a 12-bit ADC at a rate of 12 kilosamples per second. The data is then fed into a signal processing module with a throughput of 24 kilobits per second. If I use a FIFO with a width of 12 and a depth of 48K, how long can I record data for? So let me write some of these numbers up, because I know you can't hold all that in your head.
Yeah.
I'm just going to say DSP at 24 kilobits per second. And the FIFO has a width equal to 12, a depth equal to 48K.
So you take the difference of, it'd be 12 times 12, right? So
Pause 1 second. It's okay. You're quicker than others are. So, or at least, yeah, words start coming out quicker than others. So I want to give them a moment to digest all of this information. So right, so we have a 12-bit ADC that is acquiring 12,000 samples per second, KSPS, samples per second. I have a DSP module that can process this at 24 kilobits per second, kbps. They're handling them through a FIFO, because that's what I do when I have things that go at different speeds. How long can I record for before this thing fills up? Or is the answer infinity, or is it less than that? Right, because if this runs faster than the acquisition, no, there's no problem. Yeah.
So the ADC goes into FIFO, which then goes into DSP.
Yes. Yeah, so I can draw that up too. So we have ADC, FIFO, and then DSP.
So how long can we record it until the FIFO is full?
Yes, essentially. I would just ask it, how long can I record for? Because if I record longer than that, I start losing data. So the thing not to do is to confuse KSPS with KBPS. Because at first you might go, oh, well, the DSP is going faster. But it's not,
No.
because I'm generating it 12 times faster than this, right? So I'm generating data, we'll call that G, at 12 times 12, as you said, 144 bits per second, or sorry, kilobits per second. I'm processing that at a rate of 24 kilobits per second. So the rate at which my FIFO is filling is the difference between those two. So I have R is equal to 144, it's filling up, minus 24 right? So my FIFO depth is 12, so it's capturing a whole sample at a time, and then it's pulling it in and doing something with it, right? So now we have to figure out if I'm filling my FIFO at 144, I'm emptying it at 24. How long before that fills up? Well, now it's just a time conversion, right? Because this is units, kilobits per second, which we can convert that to kilobits over second. And now we can start seeing our units. And we just realize that we need to get rid of kilobits and get second on top, and that's time.
Which we need the,
Wait, hold on.
you need the number of bits in your FIFO.
Yeah, isn't that,
48K.
Wouldn't you wanna like, cause you have the 12 in there already, so wouldn't you want to make it the total space in it?
Yeah, so the total space is a width of 12 and a depth of 48.
so would we need to convert that back to samples?
Well, it depends how you want to do it. What you need to do is you have this number, R, in kilobits per second.
Yeah.
So if you can get something,
I understand we want a time value of how long that's gonna take to fill up.
And that's kind
Oh,
of, that's
okay.
where I was going with my question.
Yeah,
too,
I think we understand
To
that.
get the bits, you times 12 by 48,000 and then divide one by the other, and then you get second, correct?
Yes.
You do the.
I don't quite follow. Do you want to come up and start doodling? Because I have my own way of doing it, but if you have a different way, it's fine.
Or,
So you have the total memory is 12 times 48,000, which equals 576,000, I think I had.
Yeah.
And then you take this number and then divide it by the difference of those. And that should give you the time that you are still recording data until it fills up.
Yes, you could. Yeah, that would work.
Okay, okay.
Yeah. So what he's saying is, let's use this number, which is in units of kilobits, right? So he's gone from samples to kilobits. And then I have kilobits there, I have kilobits here. So I know that something like KB over KB over S is seconds. So then I can do that conversion and just divide 576,000 divided by this number, and that's my answer.
I feel like this should be like a differential equation. Just the way that this question says.
You can actually write it as you can write it as a differential equation. It's just easier to do it this way.
I guess these are dx's and dy, or
that's fine, I did it the opposite way. I actually took R and converted that to kilosamples per second, and then just did the depth.
Totally fine. Yeah. So the main takeaway is follow your units, because that will let you know if you've ended up with something sane. And if you end up with at least a sane number and I see what you did, I can give you a good chunk of partial credit on the exam.
4.8 seconds sound good enough?
So we think 4.8 seconds. So, and you can do a really quick sanity check. You could calculate how fast would my FIFO fill up if I wasn't emptying it at all. And that gives you a ceiling, right? So you can go, I know it's less than this. So if I'm getting 12 kilosamples per second and I have a depth of 48, then I know my maximum is 4 seconds. So that sounds wrong.
Wait,
right?
No, it goes.
Oh, no, it should be, sorry, a minimum of 4.
Yeah, okay.
So it needs to be greater than 4 seconds because I am emptying. You were correct. Yeah.
Okay.
So if I'm not emptying, I can record for 4 seconds. If I am emptying at a rate of 24 kilobits per second, I can record for 4.8 seconds.
Gotcha.
Or, yeah, if you did your math right.
So, does that change your answer then? Like, would you be able to say like
Say that again?
Because you're saying that when you aren't in pain, right, it's 4 seconds.
Yes.
So that gives us 2 different possible answers, and you have the potential to word it differently. Right?
Yeah, I could change the answer, or more likely I would ask it as a two-parter of if I run this and then run my FIFO, or sorry, if I run the ADC and then run the DSP, how long can I record? And if they can run concurrently, how long can I record? Yeah, those would give me 2 different numbers. And that would actually, even though I added an extra question there, it's almost helpful because the first one gives you the floor for reference. The last little bits, I won't cover it too in depth. I may ask questions about the generics, attributes, and the generate statements. These won't be too in depth, right? But I might ask you to do something with the attribute of like using X attribute, write the HDL to do this.
Attributes are like
The tick something.
size and, okay.
Yeah. Yeah, or I might say, I have provided you with a full adder. Use a generate statement in order to create an 8-bit full adder. Right?
Generate a little bit.
It's literally, it just says for range generate instead of for range loop. And then you can use the generate in the instantiation.
Okay.
Basically, if you had like an 8-bit adder and you store the variable and say X, you're basically saying for X, create so many adders, in which case it would be 8 adders.
And then I would create a vector that would be like carry out at, or carry at X. And then when I iterate through, it stitches together the carries in that vector.
So that's
Just go look at the attributes and generate chapters and just at least familiarize yourself with those chapters so you know where to look when you run into that problem. If you do at least that, you should be okay. The main idea there is make sure you know what it is, get a little bit familiar with it so that you go faster when you get that question. So that's really it for the review.
Did you get anything on the fast box, slow box, fast box?
I don't think so. I was thinking about it, but I couldn't figure out a good way. If there is, it's going to be like true, false, or short answer. It's not going to be long answer questions.
You can do the -1 again.
Hmm?
Or you can do the -1 again for true or false.
No, that I only did that for the one the matching thing, not true, false.
Wait, those are not.
Yeah, I asked to, I mean, it was kind of true, false, but it was asked, the question was, which of these are combinational, which of these are sequential?
Didn't you actually throw away the -1 thing anyway?
No, I used it, I think.
You didn't use it on the true false?
I did not use it on the true, false. I don't like it on the true, false as much. It's really frustrating. I have trauma back from my school days. But my advisor, every one exam, he had like 30 true, false questions. And the allocation was you had about 20 seconds per true, false question to answer it. And they were -1 if you got it wrong.
So if you got half the test right, you basically go to 0.
Yeah, it was, well, that was just part of it. So like, you could go back and revisit if you finished all the other questions, but nobody ever finished the question. So basically you read the question, and if you didn't go, that's the answer, you just skipped it. It was brutal.
Okay, like lawyers.
So I guess at this point we can jump over to the lab and get back to the project, kind of moving on it. You guys are ahead of the day class as far as course classes go, but you are behind as far as number of labs go somehow. I don't know how it happened, but it did.
So we lost a lab?
think, because you guys have just been like one lab behind as far as completion goes for whatever reason.
They
and
have 1 day before.
So you guys are not gonna have a lab on Thanksgiving. So I'm taking this as the opportunity to give you some extra lab time to make up for the loss.
So
On
that would be
Thanksgiving.
behind too.
Yeah.
So have you written up lab 5 yet?
It is in progress. Are you at that point?
I think so. Is after you get the thing reading voltages.
Yeah. Do you guys want me to start? I can go over the next lab 5, just conceptually right now.
I think that's where we're at. I don't know about the other.
Okay, I will go over conceptually. It's about,
Or you could get them started working and then pull us to a side.
yeah, I mean, if you guys want to start working, or you can listen ahead of time, whichever one you'd like. But I'll start talking about the lab 5, which I'm actually going to call lab 6 because I'm skipping lab 5, and I may like push it back in as like part of the exam in a really dumb, like the final exam in kind of a dumb way. But be aware, the lab numbering maybe get a little screwy here.
5.5.
Say that again?
I was just saying lab 5.5.
Yeah, something like that. Okay, so the general idea is that we're going to just stitch all of our modules together with some changes. Shoot.
Were you never recording?
No, I'm recording. I have what I've written for the lab in my on my desktop PC. I don't have it here. So I don't know all the numbers. So the general idea is that you have all of your little modules. You have a Uart. You have a SPY. And you have an I2C, okay? So what you're going to do, and actually I'm going to redraw this so I have enough room to keep clear. Is this whole thing is your FPGA, right? And these guys go out and interface to the real world with the I2C controlling an ADC and the SPY controlling a D to A. Right? And right now, each one of these is really essentially something like it has an I2C and it has a controller. Right? And those two work together to do stuff with the ADC. Now, the Uart talks to a PC. What we want to do is to enable the PC to control and record data from the FPGA. So we're going to be able to send commands that do things like start waveform. In fact, let's call it start stop waveform, right? Which means do something with the DAC or don't. Similarly, start, stop, record. You will also have something like set input, and that will be either to the switches or, so you can either have the ADC
Read from the switches or the DAC.
yes, so that you could manually program a DAC value, right?
Wait, set input as the switches or the DAC?
So Well, it depends. I have to finish writing the lab to figure out what it is. So we can do two different things with the switches. We can use the switches to set the DAC level, or we can use switches to generate data. And in fact, you may need to be able to do both because it's a useful debug tool to figure out what's going wrong. It's either to use the switches to set the DAC value or switches to set the output of the ADC. Because then I can test if the ADC is broken if I can set some switches and get the values out that I expect. So let me be a little more clear on that, I suppose. So the first thing we have to do is toggle switches from the DAC or ADC. The next one is toggle DAC output, which would be memory or switches, and toggle ADC out, which again is either from the ADC or switches.
Sorry, okay, question.
Yeah.
So we need to have something that, I guess I don't understand the first one. The switches are going into the DAC or the ADC?
Yeah, so yes, so the switches are either used to tell the SPI what to send to the DAC or in place of what is coming out of the ADC.
Okay. I sort of understand that.
Because I want to be able to use the switches to test the DAC or the ADC.
Okay.
Really is not test the ADC. I want to use the switches to test the DAC or to test the Uart and make sure that I'm recording the data that I expect.
Okay, so the switches, the output from the switches will go to the DAC.
Yeah, so I guess I can draw that up for you. This is kind of cheating because I expect you guys to draw this out, but switches are in the real world, right? They come into the board and they'll go connect to the SPI. Well, and then they'll also come up here.
Okay, so that first one is just toggling whether the DAC gets the inputs or the switches, or the ADC UART gets the switches.
Yeah.
Okay.
Then we also need some sort of, right, so this is some sort of master controller that is going to be controlled by the UART and send stuff back via UART. And so like this mux might make the most sense to put inside of the controller, right?
Yeah.
In fact, that's what I would probably do is I would put that mux in that controller, have both those signals coming in, and then it just updates what to do with the UART. Now, let me actually pause for a second. So start, stop waveform, start, stop recording. Okay, yes. So the next thing that I'm going to do is just for the experience of it, I'm actually going to artificially limit your UART to, I can't remember the exact baud rate that is standard, but it's something like 56K.
That seems really low.
It's half of what you were doing before.
Okay.
You were doing 112K before. So
we'll need to change our UART to reflect that.
yes, and your ADC is going to be generating data at a rate of about 78K. So just like the kind of review question we just did with the FIFO, you're going to need to put a FIFO in between here and there. And you won't write the FIFO, you'll just use the IP core FIFO.
So question, are we still doing DSP?
No, that's what I'm cutting out.
Okay.
And we may bring that back into the, as part of the final, actually.
Okay.
I think, like,
So it would just bring in filtering that goes in between this and,
right, okay.
So, are we gonna have a case where we connect the DAC to the ADC?
yes, no, they're actually going to be by default connected like so.
Okay, all right.
So that's what you're going to record, is you're going to record the output of the DAC.
Which is coming from memory.
Memory or switches.
Yeah.
And you're going to then transmit that data back to the PC using Uart and plot it with Python
Oh, no.
How do you record that data?
over Uart. So I will actually get to that,
Okay.
just about. We're almost there. Trying to make sure I'm not skipping anything yet, but we may actually be there. Okay, so the easiest way to record data is if you just use PuTTY. You can use logging and it will just save whatever comes back.
Mhm.
The other way is Python has a library, and this is the way I recommend. PySerial. That's a Python library that makes interfacing to Uart fairly trivial. And you will find hundreds of examples of how to do this.
So you can set it up so it's not just being sent to PuTTY.
Yeah, yeah, you can communicate over Python with Uart really easily.
So basically, we're taking the data from the serial, saving it to a file, and then, or saving it to a matrix or whatever.
Yeah.
And plotting that?
Yes.
Okay.
Okay, but that brings us to the challenge of the Uart, which is our ADC is 12 bits. Our
Oh, I see.
Uart is 8 bits. So you actually have to split the ADC between two Uart packages. Now, the way you might be tempted to do this is have just 4 throwaway bits and then the 4 MSBs and then the 8 LSBs,
Yeah. Oh.
just like we did. However, what I recommend doing is actually splitting for 2 header bits and 6 data bits for each packet. The reason being that,
No.
well, if you're using PuTTY, you actually avoid this problem in PySerial. But if you're using PuTTY, PuTTY doesn't speak binary. PuTTY speaks ASCII. So let's say I record maximum value on my ADC, and I get the bit 11111111, right? So I get 8 ones in one of my packets, right? If I'm doing the 4, 4, and then 8. Say I get all 8 of those as ones. That character is delete.
Oh, nice.
That doesn't save into a log very well,
Really?
right? And there are many, many issues along that line. You could literally send accidentally terminate connection.
Oh, nice.
Yeah, you don't really want terminate in your thing. You don't want like returns because those are hard to read out.
What's the terminate connection thing? Like,
I don't remember the command, but it's the end communication, which not all of them respond to depending on what your terminals are doing. But yeah, you can force terminate. So let's say that we don't want to deal with that. It turns out that if you have the first 2 bits of an ASCII as 1, 1, and then everything else, whatever, you have all valid characters with the exception of all ones,
which you don't want.
which you don't want. So what you do is you take a gate into that digit. So if they're all,
Also, if they're all one.
this may actually be
then
the
you
wrong,
have
it might be a
zero,
NOR, is that wrong?
So if they're
So what
all-
you want is if they're all ones,
Then that goes.
This
to
is
1,
zero.
So that should be an N.
yeah, I thought so. They're all ones, 0, else 1.
So you know if that's a one, oh.
So if we get 1, 0, 1, 1, 1, 1, 1, 1, then we know that the bottom 6 bits.
Well, then what you do is you get 2 packets where you have 2 bits and 6 bits.
I thought you said if we do Python.
Well, yeah, this is if you're not using Python.
Okay.
So we're 2 and 6, and then you just take these 6 and stitch them together, and you now have your 12-bit number. And you throw away the header. The header was just there to protect the data integrity.
Why can't you just send like a 0, 0, 6, and then 0, 0, 6?
0, 0?
Yeah.
Because 0, 0 has all sorts of terms that will not save into a Python or into a ASCII log. If you are using PySerial, you'll be fine.
Okay.
If you're using a putty logger or anything else that reads ASCII and not binary, and in fact, PySerial defaults to reading ASCII, which you need to be careful with.
Okay.
You need to be this. And in fact, I generally recommend formatting the data this way because having identical headers is really helpful, because later, if you really wanted, you could go and start adding like parity bits and stuff here.
So if you were doing PySerial, could you do 8, 4, and then the 4 the next one, then 8?
You could, but I think you would be crazy to do that.
Okay.
So could we just hard code that instead of the annotation? Could we just hard code 1, 0 our data?
No, because 1, 0 stuff has problems.
Great. Okay.
Yes, no, I've actually implemented this solution for Arduinos because the Arduino console stuff has the same issue. It reads ASCII, and I had to come up with a way with send 12-bit data
Okay.
without getting invalid ASCII characters. And I may be wrong on the 1, 0 as the header. You'll have to check the ASCII tables to make sure it makes sense, but I'm pretty sure those are the correct ones. But that's ASCII encoding, and then you just pull out those bits and yeah, and then you have to have your Python plotting will have to do one thing, which will have to interpret the 1, 0 as a 1, 1. Well, yeah, it depends how you do it. There's lots of implementation. You have a question?
Yeah, if we're using the Python serial, then can we just send send all 12?
There is a way. I would prefer to stick to 2 packets because I want that to be part of the control logic that you have to build.
So no.
No, yeah, so don't do that. Let's stick to the 8.
Isn't that what we have it programmed as right now, is sending 8 bits?
Yeah, but changing it to 12 would be trivial.
Yeah, changing your 12 would be, you just have to change the bit count and whatever.
So anyways, that's the system that we're building towards. I may have forgotten something simple or specific numbers, and that will be included in the lab once I finish writing it up. But you can really start pushing towards the end goal with minor changes from here. Yeah.
So the FIFO, that's just an IP core,
Yes.
And you'll want
and you'll tell us which one to use?
Yes.
Okay.
and you'll want a signal from your UART to your FIFO to tell it when to be ready and stuff. Or when to send.
No.
No, your UART will, well, it depends how you want to do it. You could set up a command that says, I want to read, and you may not always read. Or you could just have a command that says, if the FIFO is not empty, because it'll have an empty flag. If not empty, send.
Gotcha.
Right? Either way is fine. And then if I give you the requirement, kind of like we talked through today, of I need to be able to record X amount of data, how big does my FIFO need to be? Right? If I say I need to record for 1 second, how big does my FIFO need to be? Well, it doesn't need to be as big as this would require it if I wasn't sending it out, because I am sending it out. In fact, I'm sending it out almost as fast as I'm recording it, just not quite.
Gotcha.
Question.
Yeah.
So the start and stop waveform, that's starting and stop the DAC.
Yes, yeah.
Okay, and starting and stop records the ADC. Okay.
Yeah, so the video, they may not have heard because not everyone's as loud as I am. Start, stop waveform means DAC, start, stop, record means ADC. For the video people.
Oh, so you have those mixed up then.
Well, that's from prior.
Oh,
Yeah, sorry,
That's
these,
from prior, and so that's why, that's got me confused because of.
yeah, sorry, that was left over from previous talking stuff. So start, stop waveform means DAC. And record ADC.
okay.
We know that a DAC can't record.
Excellent. Yeah.
We were just clarifying.
We knew that, but did we?
I hope so.
You throw in a 4-bit record, it actually turns into a.
Yeah, so if we circle back around to doing what was supposed to be lab 5, all that would be is putting some digital signal processing here to filter out any noise. But, yes, of course.
That's what frequency signals.
Oh, yeah. So how hard is that ESP stuff? Like, is it pretty simple?
What I had planned was very simple. It was really just implementing a low pass filter or maybe a band pass. And then what you would do is I would give you a memory file, a .dat file. No, they use a different
I don't think
format.
it's DAC.
CSV?
It's not
It's
CSV.
CSV. I can't remember what data type they use, but it would give you a file that I generated, and it would be like a song or something, but it would be heavily corrupted with noise. And then you would have to build a filter to filter out the noise that is out of band, and then end up with an audio signal that you would have to be like, it is the Mario theme song or something.
So how would you heavily corrupt that data with noise?
Well,
Yeah, so that's actually really, really easy. Are we okay if I erase this?
Yeah. Like, I understand we're not, I'm just curious how
would you
you
just
do
do
it.
a convolution with the signal?
No, literally in the time domain, if I have samples, S, that's my song. If I say S plus rand, I don't know, remember the Python, I think in
It's just
MATLAB still,
a
but
number. It's pretty similar.
right. So rand X, where X is the same length as S, then instead of getting a nice smooth
Oh, I see.
sine wave, I add my sample plus a random number, right?
Gotcha.
How do you process that out?
Well, it's the transitions between how fast.
Well-
The song.
Okay.
Yeah, so what I would get if I was looking at just like a note or a tone is the ideal situation is that I would have that, right? Nice harmonic tone, whatever. But what would really happen once I start adding it is
Oh, I see. So if you take out the higher frequencies.
Yeah.
I
yeah.
got it.
So if I filter out the higher frequencies,
That makes sense.
it starts representing the original
So
sine wave.
With a, how would you do that like digitally? I'm just trying to, like, would it be like a lot of like,
Oh yeah, no, the operation is convolution. With you'll get to it. I'm sorry, I'm trying to figure out how to not overcomplicate this because you'll get to it in like DSP.
I'm asking
but-
about, like, how would you unmix it in VHDL?
Oh yeah, no, you would convolute.
Oh.
So this operation to make noise is just add in the time domain.
Mhm.
If I want to get rid of noise, I just create a filter to convolve those samples with. And then I do a convolution with the low pass filter and it goes away.
So how would you do that?
So low pass filter is like a vector itself.
Yes.
Oh, that's interesting.
Okay, draw a low pass filter.
So think of normal convolution. So say we have A and B, you convolve them together to get C.
Yeah.
Instead, B is now a vector that represents a low pass filter. You convolve A with that low pass filter B to get the low pass signal C. Does that kind of make sense?
Yeah.
So
Yeah, so low pass filter,
it's just the
frequency domain,
Yeah,
amplitude,
right.
looks like that.
What does it look like in time domain?
Do an FFT. Right?
Right. Well, so would it be like a cone?
Filters are really hard to visually.
Yeah, unless I've been teaching it recently, which I haven't, I have a hard time remembering it. They're not hard. One that you can do, one of the simplest filters is a rolling average filter, where you just take some section of it, you take the mean of that, and that's your new point. And then I move that over and take the average, and that's my new point. And I move that over and take that.
That's what I was asking. Like,
Yeah.
how do you implement in VHDL? That makes
Yeah, so that is one of them. That's a moving average filter. It functions like a low pass filter really well.
Are there any situations where that one screws up monumentally?
No, it's just not optimal.
Okay.
Because the roll off is really poor,
Mm.
where you want a really steep roll off.
Gotcha.
So the higher order of the filter, the steeper the roll off gets.
Yeah.
But there's more to it than that, which you'll get into eventually, which is a lot of times the real filter will look more like, it'll have ripple,
Like,
and then it'll have a peak, and then it'll plummet, and then it'll have ripple.
or butterworth.
Well,
Yeah.
Well, the advantage of the butterworth is to not have that ripple.
Oh, cool.
Is to be linear.
Yeah, so
But it doesn't have those good,
So you'll need to make your design decisions. And a lot of times what you'll do is you'll actually generate the filter in like Python or something, and then just load that into memory, just like you load it up, and use that for the convolution.
well, that moving average
That's actually really
filter
interesting.
that you're talking about makes sense because when you have, say, the op-amp configuration where in your feedback loop, you have a capacitor and a resistor in parallel that acts as a low pass filter because it's an integrator.
Yes, exactly. And that's what
That's exactly. that's
same
what-
operation.
But you can only get a first order filter out of that and get that makes it a lot.
Yes, exactly.
Oh, I actually never thought about it like that.
So your capacitor is acting as a register that's adding up the average, it puts it back into it.
If you like it, it's easy to go the other way, but yeah. So anyways, you'll get into more filters. They get really complicated really fast, but I can actually send you some recommended readings if you're really interested in that stuff. Because this was my master's degree.
Really?
Yeah, so like and in fact, even my bachelor's degree was tons of signal processing filters and that kind of thing. So yeah. Someday, maybe I'll probably give a talk at some point. I don't know if you guys will see it, depending on what class I do it in, that talks about some of my signal processing for radar, just because radar is applicable to here. I actually developed a lot of radar stuff for the University of Physics department that they were using for astrophysics research, but.
What's that, like, set of talks they always do here for
The symposium?
yeah, are they doing that this semester?
We're not doing anything like that. So the IEEE, so I'm the IEEE advisor, that's the
Oh,
word.
you took over for Trample?
I did. So we're not really doing anything right now because we don't have a lot of people that can take the time to do video ones, and we're not sure what the turnout would be anyways because people are still kind of in upheaval. Next semester, we're looking at doing video, and then we'll get back to the in-person stuff next year, hopefully, if the vaccines work out and COVID stops being such a big issue. I don't know, I might do a video one that just kind of talks about some of the past research that I've done, just because it is really interesting and relevant. And even for you guys that have just, as long as you've kind of taken signals, or at least well into signals, I think you can understand a lot of it. So like one of my senior project was developing an image processing algorithm for detecting radar signals, which was really interesting. And it combined like linear estimation and kind of things like that into one radar system, which was really interesting. Yeah. So they all really apply, and it's kind of fun when you get into signal processing because everybody needs it. So you can kind of touch a bunch of different fields for all sorts of things. So I've done it for cameras, and I've done it for radar, and medical devices.
That's a class I really want to take, but just with my graduation path, it's impossible.
Yeah. So some of you that will graduate with your bachelor's, go on to industry, and come back for your master will be treated to some delightful courses, I'm sure. I had a course called Software Defined Radio, which talks a lot about filters, specifically adaptive filters. How do you change the filter based on data that you have? Right. So conceptually, one of the interesting ones is if your data is highly susceptible to interference, then you can send what we call a pilot. And we know what the pilot is. And we can say, okay, so that was supposed to be a 10110, and it just wasn't. So what kind of filter do I need to make in order to turn it back into a 10110? And then once I've determined what that filter is, I use that filter on the rest of the data to clean it up. But you could also do pilotless recovery, where you can use the data itself to begin estimating what we call it the channel, so what the corruption looks like, and build in a filter that changes over time based on a changing channel. You can imagine this is really useful in things like cell phones, where I walk out the door and suddenly the wireless environment is significantly different than in this room. It is also helpful if I have like an implantable lead, and I have like a pacemaker that's talking to, I don't know, some sort of data device that's telling me if I had a heart attack and calls 911 automatically, right? As I move around, that pacemaker moves a lot, and we might disrupt that channel. And so we want to be able to change or adapt our filters depending on how our environment changes. So that'll be a course that I develop in the future at some point too.
Do we have the skills right now to make a radio?
Yes.
Is that pretty much just a filter with an adjustable thing?
It is simplest form, yes.
And then you just get a really long wire, you amplify that signal.
A wire of the correct length, yes.
Oh, the length matters.
Yes. Yeah, if you take, you should get that from EMAG. I don't know if one or
I
two.
haven't taken that.
Okay, yeah. That'll talk about how the relationship of the wire to this frequency matters.
So what are the frequencies of FM, you know?
They tell you in the name.
Is it
X96 is 96.
well, is it like gigahertz, megahertz? Mega?
Is it FM megahertz?
Is it, or is it kilohertz? I forget.
Because radio waves are pretty short. They're like long. They're really long, right?
Oh, you're right.
I think they're kilohertz. Yeah, and long means low frequency.
Right. No. Long waves means.
Yes.
Long wavelength means low frequency.
Right.
Yeah, the wavelength is inversely proportional to the frequency.
Okay, I must have gotten that like mixed up again.
Yeah, and it ties back into frequency and period, right? The period is tied to the wavelength
Right.
at a 1-to-1 correlation.
I just said brain fart right there. Long and short.
Okay, so anyways, that was a bit of a sidetrack. I guess.
But how do you tune if the length tells you what frequency, how do you tune that?
Well, because there's a band the general band that your antenna is.
Okay,
designed
so
to
your
accept.
antenna, okay, all right.
Yeah, so
It's a general bandwidth that it's close to, right? Because it can't exceed way out from it, right? Because they're
Yeah.
all within,
No, that makes sense.
you know, certain bandwidth.
yeah, so my antenna, the frequency response might look something like this. And so I have, and they do fight over this. In fact, the radio stations fight over who gets this spot
Yeah, I mean, that makes sense. Yeah.
because they want the best signal for the average car antenna,
Which is around
essentially.
like 100.
And then, yeah, so you'll notice that the radio stations get really bad once you get down into 70 somethings, right? And it's partly this. Part of it is actually the atmospheric conditions, which at certain frequencies, air becomes more or less opaque.
you
And
can
so
want
that is also a consideration. So even though your antenna has this, your channel might do things like this. And you'll get like one really bad frequency because it interacts with the air in a negative way.
So are you saying pollution can actually influence your radio?
Yes.
Oh, that's cool.
Yeah, because it's all.
Actually, it's pretty cool.
Yeah, so
But when you take EMAG, you'll do boundary conditions, and that will later play into, when you change boundaries, what happens to your signal and attenuation, reflection, all that.
That I do remember.
yeah, and then you'll have other various things. So like water vapor is a big issue that you have in like cell phone communication. When they were trying to look at the 5G stuff, they're really running into like, it doesn't go very far because suddenly water vapor starts being nearly opaque to it. And so you need more towers for 5G than you did previously.
So that-
The benefit is the houses become invisible. So you no longer lose signal because you walk inside of a brick building.
Oh, so they,
Well, and you remember in physics too, Jason, right, when you would talk about things such as, what is it, infrared antennas, right? Where they can be mesh, right? And what matters is that space in between, how it looks to it, even though there's mesh at that frequency, it looks like a solid wall to it that
Yeah.
it reflects off of. So like the 5G, at that frequency, the walls are translucent, sort of.
gotcha.
Yeah.
So the 5G is almost not like, well, it's like, yes, I have shorter range, but everything inside that range is going to be covered.
Potentially. I mean, there's tons of variables that goes into it, but yes.
Okay.
So what's the difference between 4G and 5G? Is it
It's
just
just
increase in
generation.
frequency?
It's not just frequency. It also has to do with the protocol inside of the communication.
Oh, okay.
Because some people think that 5G means 5 gigahertz, but it's just the generation.
That's what I
Yeah.
thought.
So it has to do with like the entire standard of how do we
Okay.
communicate using 5G. Sorry, so we have to ask, what is in the packet header? What kind of filtering do we do typically, right? That kind of thing.
Don't they
And
already have like
designing
6G like
the
stuff?
antenna that
Hmm?
goes in
Don't they
your
already
phone,
have
right?
6G
Because
stuff?
Yeah.
pretty much your whole
Yes,
phone acts as the
but
antenna.
Because there was a
it's
big
getting
kind of a-
confused
Yeah, you gotta-
because now like one of the big push that they have is what they call Mimo, which is multiple input, multiple output, or massive input, massive output, depending who you talk to,
Yeah.
where you, instead of having an antenna and using a frequency, you start using many antennas, many frequencies, and chopping it up essentially to send more
So
data.
you'd be using your 4G and 5G and like everything at the same time, pretty much. Then.
Yeah.
Like, is it-
Well, kind of, yeah. And you already do that. It's called spread spectrum, where they'll spread out your data. So you might actually use multiple channels at the same time, but the whole evolution of the communication protocol is happening rapidly, and it happens both on the EMAG level and on the DSP level.
That is one sort of study that I do not want to get into.
Which one?
Communication.
Oh, I love it. It's a lot of fun. But it does have challenge. And
I feel like it's just so competitive right now.
Everyone's got their own thing.
it's competitive in the sense that the employers can't get enough relevant engineers.
Okay, so it's not really a big issue. It's like-
As an employee, no, it's wide open.
Gotcha.
Yeah, it's one of the few fields, like, so a lot of my friends, because I'm up at the U, are foreign. Communications is one of the few fields that they all could go get jobs in, because they can't get jobs in defense.
Right.
So they get jobs in communication because that's who's
And
hiring.
what companies, like, besides
so
cell
it's
phone
not
companies do communication?
So most of them, in fact. So like Intel and AMD both hire people for it. And then they have, shoot, why can't I think of their stupid names? Normally I get them confused. Now I can't think of them right now. What'd you say? Qualcomm, yes. Qualcomm and the other comm.
I don't remember what the other one is.
Rom-com.
I can't remember. There's another something comm that are both just major telecommunications companies.
Yeah, okay.
Um,
And
but
then-
L3, they're a defense contractor, but they hire for stuff like that. So, I mean, even Texas Instruments will hire for it because they'll develop chips that are just drop in place to do stuff.
Okay.
Okay. And then there's Comcast and all those places that are doing it.
Yep, Comcast hires a lot, and more they're hiring optics engineers as we go to fiber. Especially, and one of the big ones that you'll actually see that pays money is what we call wireline communication, which is wired communication for data centers. Yes, so massive server farms need to send data all over themselves at insanely high rates. And you start getting into competitions. They measure it, like one of their big measurements they obsess over is picojoules per bit transmitted. And so they pushed that thing down in the last couple of years from dozens of picojoules to individual, like single digit picojoules per bit of data transmitted. And that's not enough. It still generates too much heat and too much energy just to pass the data.
So at what point will stuff like that be completely outshined by quantum?
Maybe never. We don't know. I mean, quantum is still too up in the air to really know.
Yeah, because it's a lot different than a commercial type of computing, so until we get it, like we find out sort of commercial setting, then
And it may just never matter, right? It may be quantum is restricted to business entities and they do that, and your consumer goods are still hardware as we know it forever, right? Potentially, because it's just so much cheaper.
Yeah.
Because realistically, if you think about it, how much faster does your phone need to go than it is?
Right.
Well, if we start doing VR, it needs to get faster, but one order of magnitude faster is probably enough.
And then we find another, I feel like one thing that's
Open up your, I usually open up
is like,
the other
all these
test
things
bench,
are
'cause I
like,
don't know the
but like,
exact
what happens if
syntax.
this pops up in the
So
night, doesn't
open-
become completely useless?
It will never matter because the issue is, I don't think it will ever matter, is because there's always fields looking for talent. And if you get displaced as a signal processing engineer, for example, it applies to everything. You will find a new niche, right? And you may have to take a course online or something of quantum signal processing. And then suddenly you have all of that experience as a signal processor, and now you're a quantum signal processor, and it doesn't matter. I mean, optics went through the same thing, is nobody was graduating enough optics graduates, so they were stuck hiring either physicists in optics who don't know anything about engineering, or engineers and teaching them optics. Well, they liked to go with the latter. They liked to just take DSP engineers and so here's a laser, go, right? And then the engineers start iterating on it and start doing interesting things with optics. Optics is wonderfully interesting, but I suck at it.
That's what's the other.
Yes, and it's hugely valued that we have Dyer here, because optics is a big field coming up.
Because optics is like, that's one of those things that like, an optics.
Okay, so you do need process, okay.
What
So I was like,
need to do, but they also do optics.
well, so,
Or like digital signal processing goes optics.
Yeah.
It's kind of like how it's analog
And-
with all the digital. but
And
digital
similar to
signal-
how I was talking about with like radio, right, or radar, in fact, you have the electromagnetic side and you have the DSP side. That's still true for optics. You have EM people working on it and you have digital people working on it. And they don't necessarily have to know the other side very well. They just have to have a shared vocabulary.
Gotcha.
Yes, the relationship is, what do we absolutely need?
oh, wait, no, hold on, that
The
is the
analog side of
outside.
things, and then like the rest we can get away with just digital, right?
Yeah.